Okay, welcome to the heliophysics big year. It's a celebration of the sun in 14 months, and each month we take a particular theme that has to do with the sun and heliophysics. Don't rush off to your dictionaries and look up the word heliophysics. It's not in there. It's a fairly new term. Uh, it's basically the study of the sun, the processes in the sun, including the energy production and all of the sordid details of the interior and the surface, and also the production and distribution of the solar wind, which reaches all the way out beyond the orbit of Pluto and collides with the interstellar medium. So it's basically a pretty comprehensive subject. It also includes interactions with the Earth's magnetic field and the magnetospheres of other planets. So it's kind of the motherhood physics theory of everything in the solar system that's essentially non-gravitational. That's sort of the way I like to think of it. The big year started with the annular eclipse in October 23, and it concludes with the close approach of the Parker Solar Probe with the Sun, one of its many closest approaches, but this is sort of the penultimate closest approach, I guess. And that happens on the 24th, next month. The themes we've kind of come off, and now we're in the November bonus science theme. Well, the bonus science is that since we're talking about the Parker Solar Probe in December, I thought it would be good, since we haven't really talked about it too much, to discuss the idea of the solar wind and why that's important. For you educators, we tend to organize things in the heliophysics division kind of in a shorthand. You can think about it as three big questions. What causes the sun to vary? How do the Earth and the heliosphere respond? And what are the impacts on humanity? These are sort of the three big core questions that you can usually hang most of the mission goals under in one way or another. Under these, in the framework for heliophysics education, which we've created at NASA Heat, you can also identify subsidiary questions under each of these big questions. And these subsidiary ones map rather nicely into the national science standards. And those particular ones are listed in parentheses here. You can see. The red highlighted ones are the ones that are likely to map pretty well into what we're going to be talking about today, which is not the radiation that the sun produces, but the particle streams that it emits. So it's a second form of material that propagates out through interplanetary space and affects planets. And in a one way or another, we call this part of the so-called space weather experience. And I'll talk about that a little bit later as well. The solar wind is kind of an interesting thing. We didn't even know that it existed until the early 1950s, when astronomers began to puzzle why it is that the comet tails, which they knew there were two different types of tails, why it is that the ion tail seemed to always point in the direction of the sun, no matter where the comet happened to be in its orbit. And they worked out that basically it couldn't be radiation pressure, it couldn't be sunlight pressure. Excuse me. So this is where the concept of the solar wind came into play. It had to be some kind of a particulate stream that was pushing the ions from the comet's head into a kind of a windsock orientation, flowing away from the sun. Well, in 57, Eugene Parker sat down and devised a set of equations that tried to essentially talk about sort of the fundamentals of what a wind like the solar wind apparently would look like. The fundamental equation is called the Navier-Stokes equation. And basically, it sort of identifies how particles as part of a gas will flow like a fluid, if you will. It's a fundamental equation that's even used in aeronautics and in other areas where you're talking about aerodynamics. But in this case, it applies to very low density plasma, neutral particles in this particular case. And the thing is that all this is Newton's F equals ma, force equals mass times acceleration. But in this case, instead of mass, we talk about the density of the gas. And instead of acceleration, excuse me, excuse me, we just use the mathematical term dv dt. But basically, this is F equals ma. It's Newton's law of motion applied to gases that have pressure, that are operating under gravity, which is that little G symbol that you have there, and are also doing other things which are characterized by that third term. Now, it's an interesting thing that in many theories that are mathematical in physics, very often those theories are in the form of fundamental equations. And the way you connect up with the actual physical world is identify solutions to these equations. Now, the interesting thing is that you're starting with an equation, and the solution to the equation that you're interested in also happens to be an equation. An example of this kind of strange situation is, when you think about old style solving the quadratic equation to find the two roots, the x-intercepts, as it were. Think about an equation where instead of x-intercepts, your solutions are other equations, okay? And those equations pertain to the specific kind of physical situation that you're trying to model. An example of this in relativity, in Einstein's relativity, is that he proposed a general theory of gravity as a mathematical equation. One solution, mathematical solution of that, would be the black hole, which represents a kind of equation that is the solution to this. And you can probe that equation, and from that you can identify the structure and the details of what a black hole looks like. Well, in this particular case, there is a very simple, and that's the one that Earth scientists use quite a lot. The reason that we have the atmosphere of the Earth being dense at the bottom and very rarefied at higher latitudes or elevations is a particular solution to this equation, where you're talking about a single temperature neutral gas, no charged particles. Gravity is operating in only one direction, that is from the bottom to the top, from the surface of the Earth up into space. The gas is in pressure equilibrium so that there are no winds, so you don't have any movement. There's no flow of matter, that is to say, the Earth's surface isn't producing this gas, which then flows up in the atmosphere. Instead, the atmosphere is a fixed gas of particles throughout all of this. And basically, the system is static in time. It's not evolving, it's not doing anything. So that gives you an equation that gives you the density of the gas from the bottom at the surface of the Earth all the way up into the upper atmosphere. And one finds that it decreases exponentially. And this is a solution that atmospheric scientists use all the time. Turns out that if you go up about 12 kilometers, the equation tells you that about 80% of the Earth's atmosphere is below you. Okay, so that's an interesting factoid that comes out of this. But here's another solution with slightly different conditions, like these bullet things here. In this case, we're going to talk about a gas that's heated from the base. We're going to allow mass to flow into the base of this system. And we're going to allow there to be a difference in temperature between the base and out into interplanetary space. It turns out that the Navier-Stokes equation under these conditions provides not just one solution like the atmosphere of the Earth solution, but it provides you with 5 different classes of solutions, 5 different equations that describe how the speed of this gas is going to change as you go farther away from the sun. Um, I've represented these solutions in a single, which makes it look extremely complicated. And to some degree, it is if you're not familiar with looking at multiple functions on the same plot. Excuse me. Let's take a look at solution number one, Roman numeral number one. The distance from the sun changes from 0 on the left to 5 times the radius of the sun on the right on the horizontal axis. And it changes from 0 up to a factor of 3 in the speed of the particles relative to the sound speed. Sound speed of a gas is a fundamental property of how fast things are moving within the gas. This, however, is talking about the bulk motion of the gas as it's moving through space. So these are sort of two different things. But it's very convenient to characterize the bulk motion in terms of sound speed. We do that all the time here when we're talking about, jets flying at Mach 1 or Mach 2 or Mach 3. You can think of this in the same way, that this is essentially showing the speed of the solar wind from Mach 0 to Mach 3 relative to the sound speed of the solar material. Okay, so anyway, if we follow how line number one, curve number one is going at 0, 0, it starts to go away from the sun and it increases in speed. So it's rising, rising, rising. It's not rising very fast. It increases in speed, and then it reaches a point where it sort of starts decreasing in speed again, or it increases in speed the whole way, but now the distance from the sun is beginning to decrease again. So it's like this gas moves outward from the sun very rapidly, but at the same time, it's starting to fall back onto the sun. Well, that's not a solar wind solution because that's not going to get you to the Earth. On this scale, the Earth is out at about 250 of these units on the horizontal axis. So that's not going to work. There's another solution which is identified as Roman numeral 3b, where near the sun, it starts out going at Mach 3, way up at the top there. And then as the gas gets farther and farther away, the gas starts slowing down, slows down, slows down, until by the time it gets out to 5 times the radius of the sun, it's barely going much above the speed of sound. So this is a decelerating solar wind. That one is going to arrive at the orbit of the Earth, but at a very, very, very slow speed. In fact, the speed of the solar wind as we measure it out here by the Earth's orbit is between 2 and 3. So we can't look for solutions that are 1, Roman numeral 1, Roman numeral 4, or Roman numeral 3b. We have to look at one of these other 3, which is 3a, Roman numeral 5, or Roman numeral 2. Let's take Roman numeral 2 first, which is really kind of weird looking. That's that parabolic thing that you see there. This is a kind of a weird wind because it starts out far away at a slow speed, and then it accelerates as it gets into the sun, traveling at Mach 1. And then it picks up speed again and flows back out, far beyond the area of the sun, and just keeps on accelerating. Well, that's an interesting solution, but it's not physical because that's not how things would work if you're actually putting matter into the base of this material and having it go out from the surface of the sun. It wouldn't look at all anything like that because we're not going to start this material way out at 5 times the radius of the sun and then have it somehow fall into the sun and then going back out again. The wind has to be going out the whole time. It has to be starting at the surface and going out from there. So 2 can be eliminated, which leaves 3a and 4 and 5. These are interesting solutions in a way. 3a is kind of strange because it starts out close to the sun, way at the top of this diagram here by the number 3. And it's basically slowing down the whole way until it gets out to about the distance of the radius of the sun away from the surface. All right, and that's at this point here. And it's slowed down to about a Mach 1.5, 1.7. And then it starts speeding up again and picks up speed. And eventually it winds up at the distance of the Earth, traveling at a pretty good clip. Well, what's wrong with that kind of a solution? Well, again, we want our solution to start out at the solar surface. We don't want it to start out at some other place and do some kind of a strange deceleration before it picks up speed and travels outward. We want it to be continuously accelerating the whole time and start out as essentially as close to the sun as possible. We know that the inner corona is at a distance of about a quarter of the radius of the sun away from the solar surface. So that means that it has to be down here at about a quarter of the radius of the sun away from the solar surface, traveling at fairly low speed, and then it has to pick up speed the whole way until it finally reaches the orbit of the Earth. And the only solution that does that is solution number 5, which is called the Parker solar wind solution. And that's a little bit of the argument for why that particular solution is the one that we choose. There are other mathematical considerations, but this is sort of the easiest one about heuristically. The nice thing about it is that there is a point at about the solar radius away from the surface. That puts it at about a half a million miles away from the surface of the sun, where the matter in the solar wind, which is still mostly in the corona at this point, is starting to accelerate outwards and has reached the sound speed. It's now at Mach 1. Okay, and it does that somewhere within the corona of the sun, and that's actually a region that we're hoping to get more information about with the Parker Solar Probe, and so that's why we're very excited about the measurements that it's likely to start making, and some of the conclusions we'll be able to derive from those, essentially constraining exactly where this transition point is. And a little bit of the physics about what is going on in that region to cause the acceleration of the solar wind. So that basically is the basic idea of the solar wind. You know, why we have it. It turns out it's a very hot corona at 1 million degrees. The gravity of the sun is fairly weak by the time you get into the outer corona. And so material that is there is likely to boil off just like the steam in a boiling kettle. So if you think about it in those terms, it's pretty straightforward. The sun ought to have something like a solar wind. So that's the general kind of a concept. Now, what is producing the solar wind is an interesting question. It's one that astronomers, solar physicists have been working on since the 1960s. Of course, the problem is that we've been very data starved. We haven't been able to see either the corona or the surface of the sun in enough detail at enough wavelengths to really understand what the phenomenology of the solar surface and the corona are. We see little intimations that there's structure here and there that changes in time, but we really can't do the proper measurements, to determine magnetic field strength, particle density, temperature, composition, which are all vital ingredients to creating a very accurate model of the solar wind. That has all started to change really in the 21st century when we have been able to make very, very high resolution measurements of what the sun is doing, and also kind of figuring out exactly where the energy comes that's not only producing the corona and keeping it hot, but also the mass flows that are involved, where they come from, that are producing the solar wind itself. The Hinode spacecraft back in 2006 in the X-ray region of the spectrum was able to image the sun and find what they called nanoflares. These are little bright points of X-ray light that you see all across the surface of the sun, whether you have sunspots present or not. They just seem to be, a constant, very widespread feature of the sun. You could count how many there are. From the X-ray emission, you could figure out the temperature of the plasma. You could also work out a little bit about the strength of magnetic fields in these things. And they are very unlike sunspots. They're concentrated regions of magnetic field that's changing very rapidly in time, producing very, very small flares, not the gigantic ones that you hear about, from time to time now. But these are very numerous and very low level flares, but there are so many of them that they add together to really produce a lot of emission in the X-rays and potentially a lot of mass flow as well. The more recent observations since 2022, 2021 have actually been able to trace some of these interesting flares and prominences and plumes from the inner corona and solar surface all the way out into the solar wind itself, which is imaged by the SOHO LASCO instrument and also other instruments that we have. So you can actually see on the big screen the LASCO image, and then you can map that into higher resolution images that we have of the inner corona. And you can identify what structures in one area correspond to features in the other in a kind of a continuous way. And this picture shows an example of that. And you also see these streamers. There are plenty of these streamers that trace through all of these images. Here's one that I've identified with the yellow arrow. It goes all the way out. And there are others, if you look at the LASCO image, you can see they all resolve into numerous plumes and traces. And then if you trace them back into the inner corona, you can actually see features that probably are the root cause of those plumes. And here is really a super resolution and here you can see photospheric filaments, okay, which are all over the surface of the sun. And now you can see them not only on the surface, but when you see the edge of the sun, you can also see them extending into these very fine hair-like plumes that extend into the corona itself. So we now think we understand that the origin of the solar wind and a lot of the material and heating of the corona is essentially caused by these numerous plumes of plasma which are being ejected by the surface of the sun. And so now the hunt is on to find out the origins of these and the mechanism that's producing the release of the plasma and the magnetic changes that accompany that. So let's do some interesting sort of math. We're going to talk about jets. Each picojet is a cylinder about 200 kilometers in radius. That's what they call these very, very fine scale plumes that you see in the corona in the previous image. And we're going to see, first of all, how many of these would cover the entire surface of the sun, just to get a handle on how many of these are likely to be present if you covered the entire surface of the sun with them. So we first figure out the area of the surface of the sun using 4 pi r squared. Radius of the sun is 690,000 kilometers. So we get about 6 trillion kilometers squared for the total surface area of the sun. The area of a picojet, we're going to use pi r squared, where r is 200 kilometers. And for that, we get 130,000 kilometers squared as the area of one of these jets. If we divide the one number by the other, we get something like about 48 million of these jets could cover the entire surface of the sun pretty nicely. So that gives us sort of the maximum scale of how much of the surface could be involved in this jet-like behavior. We know that from measurements out where we are, and assuming that the solar wind goes out in all directions from the sun, about 1 million kilograms every second of particles leaving the sun to create the solar wind. And so now the question is, if we've got 48 million of these picojets, how much matter is being produced by each of these picojets every second? So to do that, we simply divide the 2 billion kilograms per second by the 48 million picojets, and we get essentially 40 kilograms per second is essentially the flow that we need from one of these jets to give us the current solar wind. 40 kilograms per second, is is not very much. It's about the mass of a human, very crudely, and that's coming out every second from close to 50 million of these filaments on the surface of the sun. We know that the entire surface is not covered by these filaments. In fact, these filaments tend to congregate along the edges of these so-called granular cells. The granular cells are convection cells on the surface of the sun. You can see these with very good telescopes. Even amateur astronomers can see these with very narrow band hydrogen alpha filters on telescopes that are at least 8 inches in aperture or larger. And in fact, that's sort of a high water point, for amateur astronomers, that look at the sun. How well can they resolve the granulars, and can they actually consider making a movie of these granulas as they change? The flares, the picoflares, seem to be oriented along the boundaries of these granular cells in regions where the material that's upwelling floats out from the center of the granular cell and then dips back down into the interior of the sun. And that forms this sort of a dark zone that you see around each of these granulars. Well, it seems that these picoflares and filaments tend to congregate in those zones where the flows are converging back down into the interior of the sun. And these flows are going to be dragging magnetic field with them. So it provides a very dynamic environment of converging and compressing magnetic fields to form a very nice and potent state for releasing energy and converting it into heat and mass flow. Each granule is about 1,500 kilometers across. Another information slide. We call the structures that we see at the boundaries of these granules, they form a kind of a network in the chromosphere. And you can see this network very clearly in the white regions here. The dark areas are the actual granular zones of convection. And the white regions are the areas where the flows are converging from neighboring granules and converging back into the center of the sun. So it forms a kind of a network. And if each of these granules is about 1,500 kilometers across, you can now figure out how many of these granules there are. The average distance between the picojets, if they're constrained by the granules, are also going to be 1,500 kilometers, and gives you some information here. You can figure out essentially how many jets are present in the surface of the sun, in the chromosphere, if you assume that they're related to these granule boundaries that are essentially 1,500 kilometers apart. And what you do is basically use the fact that the separation between things, if you know what the area is per unit, the separation between the centers is just the square root of the area. And I've shown a diagram here where if you have a square that has a side d, the area is d squared. The square root of d squared is just d again, and that happens to be the distance between the center of one square and the center of the other. So if we know that these granules are 1,500 kilometers apart, we can actually figure out roughly If there's one of these picoflares per granule, we can figure out essentially how many of these jets should be present if they're related to the granule boundaries. So again, the area of the sun is 6 trillion kilometers squared. The area of a network cell is 1,500 square, or 2.2 million square kilometers. And so again, dividing the one number by the other, we get something like 3 million of these potential sites for these jet filaments. All right. So to create a solar wind that has 1 billion kilograms per second, how much mass has to flow in each jet? If there are now roughly 3 million of these jets, well, dividing the one number by the other, now you get about 740 kilograms per second as the mass flow out of one of these jets. There aren't as many of them because they're limited by the geometry of the underlying granular convection cells. They just don't sprout up anywhere. And so we now have to put in more material flowing out of these things because there are fewer of these jets in our estimate. So you get something like about 740 to 800 kilograms per second as sort of the typical mass flow for one of these things. Now, let's take a look at energy, and that's kind of an advanced concept here. It turns out that when opposing magnetic fields collide or are pushed together in a plasma, they tend to want to change their geometry and essentially annihilate some of the magnetism in order to produce a simpler magnetic field shape. Okay, and so essentially what you do is the opposite polarity lines are coming together, they meet up, and they form a simpler shape. And as a result of that, that produces an exchange of energy between what's stored in the magnetic field there and the heating of the local plasma, which is forming currents and doing all kinds of interesting magnetohydrodynamic things. We can calculate the energy that's involved. It turns out that the available magnetic energy in a particular volume is simply the density of this energy, magnetic energy, which is determined by the square of the magnetic intensity divided by 8 pi, multiplied by the volume in the region that contains these opposing magnetic fields, which are about to reconnect and change their geometry. So the cylinders are 200 kilometers in radius, and say they're 10,000 kilometers tall, and that they have a magnetic field of a strength about 100 Gauss. And so the question is, what's the available magnetic energy in such a structure? Here's a kind of a cartoon sketch of what that looks like. You have opposing polarities coming together in a volume, in a cylindrical volume. Just an estimate, we're creating a toy model just to get some idea within a factor of 10 of how much energy is involved. And that's a completely reasonable thing for a physicist to do. It's usually called a back of the envelope calculation, just so they can get an idea of what particular domain of energy and mass and temperature they're operating in. Anyway, okay, if we b squared divided by 8 pi with b as 100 Gauss, then we get a value of about 40 ergs per cubic centimeter as the energy density. And the volume is 200 kilometers squared by 10,000 kilometers tall. So that gives us something under about 1.3 billion cubic kilometers. After we've converted that into cubic centimeters, we get a volume that's about 1.3 by 10 to the 24 cubic centimeters. If we multiply that by the 40 ergs per cubic centimeter in the top, we get that there's about 5 by 10 to the 25 ergs available for each of these flare volumes. Now, that's a kind of an odd unit, but put it into sort of more. It works out to about 1,200 megatons of TNT for each one of these flares. So that's an awful lot of energy that's potentially available. Of course, some of that energy goes into heating of the local gas to turn it into a plasma that emits in the X-rays. That goes into increasing turbulence locally and things like that. But the amount of that is going to come out just as kinetic energy in the plasma leaving the flare itself and being ejected into the corona as the solar wind. We don't quite know because we don't have really enough data yet to know what's called the calorimetry of one of these flare events. We'd like to know the density of the gas at the base of one of these picoflares. We'd also like to know the speeds of the particles and a little bit of the energy balance that's involved. How much of the energy comes out as radiation, how much comes out as local particle heating and flow, and how much of it actually comes out in directed filaments of energy going into the solar wind. But we know that we have plenty of this available, and basically one of these flares happens each, every second or every minute. So they're going at a very, very appreciable rate to give us the solar wind that we see. So this is kind of a kind of a rapid view of the things that are involved in creating a toy model of the solar wind. It gives you a little bit of a flavor for how we've created a solar wind model theoretically by looking at 5 different solutions of a fundamental equation and basically looking at each solution and seeing which one is physically realistic and which can be eliminated. It always amazes me that very often physics is like that. You have a fundamental equation, you solve it for a particular case. The solution is often a set of equations, and you have to essentially identify which of those equations pertains to your particular case. The very same equation in relativity that gave you black holes also gave you Big Bang cosmology, gave you wormholes, it gave you gravitational lensing, it gave you gravitational time dilation. A lot of things came out of that one equation as different solutions to that equation pertaining to different physical phenomena, some of which had not been seen before. They actually did the solution. So anyway, that's all I've got to report tonight, which is just as well because I'm starting to lose my voice. But next time we're going to talk about the Parker Solar Probe and a little bit about what it has found so far, which is very fascinating. And, make a prediction for what it's likely to see when it makes its closest approach on the 24th of December. So that's basically all I have to report at this point.